Hello and welcome to PlanetSpace. My name is Virender Kumar and I am former director of a unit of ISRO which is located in Ahmedabad in India. I have been making YouTube videos in Hindi language on various subjects, space related and science related, and there has been some popular demand that some of the videos should be done in English as well. So this is in response to those requests. A few days back I made a video in Hindi about AdityaL1 mission of India. Aditya, which literally means sun in Hindi, was a solar mission which was launched by ISRO India last September. And this January the spacecraft entered its intended orbit at L1 point. Now people ask me, what is this L1? And when we tell them, well, L1 stands for L1 Lagrangian point, and there are many Lagrangian points around Earth and Sun system. So hardly any information is conveyed to the people. And when we look through in the literature, we find that the explanations given are usually very complex. So few days back I was discussing with one of my former colleagues, Mr. Bharadwaj, and we decided to generate a video which is in a very easy language so that common public could comprehend what is meant by the Lagrangian points and what is AdityaL1 mission. So that's how we started working on it, and we devised a fairly simple explanation for this I think unnecessarily made complex issue. Let us now talk about the mission. Now if you ask me, or anybody can ask me, why did we have to send a mission to deep space for observing the sun? Why couldn't we do it from Earth itself? Well, sun can be observed from Earth in the daytime, of course, and there would be obstructions due to clouds. Dust particles would deteriorate the sensing of the data. So if we want to really do good observation continuously, if we want to observe the sun, we have to launch a spacecraft away from the atmosphere of the Earth. Now if we launch a spacecraft in space, either it orbits another heavy body like Earth, or maybe some other heavy body in our planetary system, or it can, if we give it enough velocity, it can keep going in deep space. And we don't want either of those two situations, because if we send an orbiting spacecraft, again we will have occasions when sun is not visible to the spacecraft, and moreover we would have to spend much more energy to maintain that spacecraft's orbit. And of course if the spacecraft leaves our planetary system, it is of no use to us. It cannot observe the sun. So we had to send the satellite to a location where it can continuously observe the sun without any obstruction, and it should also spend very little fuel on maintaining itself in the orbit wherever it is. Now Lagrange told us that there are points in the Sun-Earth system, or in fact in any two-body system, even Jupiter has Lagrangian points. In the Sun-Earth system there are 5 locations which are labeled as L1 to L5, where we can send the satellite and it will continue to remain at those locations without much perturbation, and we would not have to spend much energy in maintaining that spacecraft in that region. Well, let us look at this slide, and here we have shown Sun, Earth, and there are 5 points which are labeled L1 to L5, and by definition, as the Earth goes around the Sun over the year, it travels 360 degrees in 1 year. So if we want our Lagrangian points to be stable places where the satellite can be placed, that means all those points will have to travel along with Earth. This is a little bit counterintuitive, because we know that if a body orbits another body, the farther it is, the slower the angular velocity. Whereas in this case, a body may be nearer or even farther than Earth from Sun, it still travels at the same angular velocity. Well, that is the basic requirement of a Lagrangian point. So let us try to understand the physics behind the Lagrangian points, which is not very difficult. Well, let us look at this slide, and here what we have done is we have made a turntable, a simple turntable which can rotate, and at the center of the turntable we have placed a red body which is Sun, let us say, and there is a blue body which is Earth, and it is at a distance r from the center, distance r from the Sun. Now let us rotate this turntable. Well, as we rotate the turntable, and of course we are assuming that there is a gravitational attraction between Sun and the Earth here on the turntable as well. So normally if we rotate the turntable, the Earth would fly off, and if we want to maintain it on the turntable, we'll have to stick it with some adhesive so that it does not fly off. Now let us see what are the forces acting on Earth. Now in the accompanying graph, we see a blue line which is nothing but the gravitational force which is acting on Earth. So it's quite evident that on the left side, as we go far away from Sun, it approaches 0, and as it nears the Sun, its value goes very high. Similar behavior is there on the right side of the graph, but in the opposite direction. That is quite understandable. The orange line which we have shown is the centrifugal force, which is proportional to omega squared r. Now omega, if it is a constant, it has to go along at the Earth speed. We can remove it, so F is proportional to r. So as we change r, the F, the centrifugal force, varies linearly, and orange line shows that. And the green line is the resultant of those two forces, and we see that green line passes the x-axis at certain locations. Now at those locations, we can see that the amplitude of and direction of the blue and the orange, they cancel out, and there is no force acting on the body at that location, and there are 2 points in the x-axis. Now if we place Earth at exactly that distance, it will not fly away, and we will not have to stick it with some adhesive. In fact, that's what happens in the two-body system of Earth and Sun, whereby in the orbit, the Earth orbit, the centrifugal force exactly equals the gravitational attraction. That's how it remains in the orbit at that particular angular velocity. So it's a kind of Lagrangian point for the Sun and Earth two-body system. Now let us look at the next slide, and here we have our good old turntable, and on turntable we have Sun, we have Earth, and we have labeled 3 points here, 3 locations, L1, L2 and L3, and let's see what's happening at those locations. So in the graph, the upper graph on the right hand side, the top portion we have shown the force on the a body which is placed either at L1 or L2 or L3 for that matter, and if we place bodies there, so what are the gravitational forces acting on that body if the whole thing is going around at the same angular velocity, which is 360 degrees per year. Now, as in the previous slide, the gravitational forces are quite evidently behave in a similar way. Only on L1 the behavior is slightly different because it explodes right away on either direction, but it does pass the x-axis. We have orange line exactly as in the previous slide. So in the bottom graph we have shown the resultant, the green lines, and we see these green lines again pass through the x-axis. So all these points correspond to the Lagrangian points, and we have made a nomenclature for these points. The point between Sun and Earth is called L1. The point on right side of the Earth away from Sun is labeled as L2, and the one on the left side away both from Earth and Sun is labeled as L3. Well, we can see from these graphs that if we want to observe Sun, the best location would be L1, because from here the Sun can be observed without any interruptions. Whereas the US sent the James Webb mission, the JSW James Webb telescope, and they placed it at L2 because they didn't want to observe the Sun. They wanted to be facing away from Sun to observe the deep space, and the L2 location is very appropriate for that, because not only they would be facing away from Sun, they would only have to shield from one direction, from Sun direction, to keep their instruments pretty cool. And L3 of course is of no use, because even if we send something there, it cannot send data back to Earth, because it will be immersed in the noise of the Sun all the time. So that's of no use. So here we see, if we place a spacecraft in the vicinity of L1, L2 or L3, it will continue to rotate along with the Earth-Sun system at the same velocity, same angular velocity as that of Earth, and that is what we want from the spacecraft. Well, there are 2 more points, and we can see that in the next diagram. They are L4 and L5. These 2 points are also useful points, and it's possible to place spacecraft there to do various kinds of observations. And we may notice that these 2 points, L4 and L5, they make equilateral triangle between its own location and Sun and Earth. Aditya reached L1 point in January this year, and if we look at the previous slide closely, we mentioned that the L1 point is an unstable point. Now that means that if the location of the spacecraft goes a little towards sun or towards the earth, it can fall to the either side very quickly. So how do we handle that problem? In that case, we have to place the satellite in an orbit there at that location. That orbit, we can see it clearly in the slide, is perpendicular to the plane of the slide, and that orbit is a self-correcting orbit. That is, if it gets perturbed, it gets compensated by itself, and the spacecraft continues to remain in that region by and large. So that is called a halo orbit. So in our next video, we are going to discuss about the stability of the orbits at various Lagrangian points. We will talk about what the Aditya mission is going to do while observing the sun, and how that will be helping us on Earth. So see you next time in the next video. Good luck and bye-bye.